Hello, I'm Austin Mallier, and this is my second midterm for the spring 2020 semester for Physics 270. And the first problem I start with is Chapter 7, number 28, and the problem reads, a 100-gram bullet is fired from a rifle having a barrel of 0.6 meters long. Choose the origin to be at the location where the bullet begins to move. Then, the force in newtons exerted by expanding gas on the bullet is 15,000 plus 10,000 x minus 25,000 x squared, where x is in meters. And the first part of the problem is A, determine the work done by the gas of the bullet as the bullet travels the length of the barrel. So we have the mass equals 100 grams, and the length of the barrel x is equal to 0.6 meters. And we have our equation f of x is equal to 15,000 plus 10,000 x minus 25,000 x squared, and then x is in meters. And our work done is w times the integral from x initial to x final f of x dx. So I converted our integral and I split up all the different parts of the equation, and the integral is 0 to 0.6 meters of 15,000 dx plus the integral from 0 to 0.6, 10,000 x dx minus the 0 to 6, 25 times 25,000 x squared dx. And this is the work that goes along with it, and in the end I found that the work done was 9 kilojoules. For the second part of the question, it asks what if the barrel was 1 meter long, and I skipped the work before the integral because it's the same as the last problem, and found that the work done would be 11.7 kilojoules. And then C asked, what is the actual work done in part B? So the change in work would be 11.7 kilojoules minus the 9 kilojoules, and that equals 2.7 kilojoules. And then as a percentage, we do the change in work over our work times 100%. So 2.7 kilojoules over 9.7 kilojoules times 100 is equal to 30%. This would be a 30% increase in work done in part B than in part A. For my second problem, I chose problem 41 from chapter 8. And the question reads, a loaded ore car has a mass of 950 kilograms and rolls on rails with negligible friction. It starts from rest and is pulled up a mine shaft by a cable connected to a winch. The shaft is inclined at 30 degrees above the horizontal car, and the car accelerates to a speed of 2.2 meters per second in 12 seconds and then continues at constant speed. So for part A, it asks, what power must the winch provide when the car is moving at constant speed? So we start with our total mechanical energy equation, which is equal to delta K plus delta U, and then that is equal to 1/2 mass times velocity final squared minus velocity initial squared plus mgy. Then from the figure to the right, we find out that sine theta is equal to y over d. And for the height of our incline, we have y is equal to d sine theta, d being distance moved by a car. And then solving for energy of the car, we have E is equal to 1/2 mass times velocity final squared minus velocity initial squared plus mgy. And then that becomes 1/2 mv final squared plus mgd sine theta. And then we have our power equation in terms of energy. So P is equal to derivative of our energy equation. So dE over dt is equal to d over dt times 1/2 mvf squared plus d times mg d sine theta, and that equals mv times dv over dt plus mgv sine theta. And then we do the rate of change in velocity. So our du over dt is equal to 0. So the equation becomes p is equal to mv times 0 plus mgv sine theta, when that equals mgv sine theta. And then inputting the values, we have power is equal to 950 kilograms times 9.8 meters per second squared times 2.2 meters per second times sine 30, and that gives us 10.2 kilowatts. And then B asks us what is the acceleration of the car. And our acceleration is dv over dt, and then that equals 2.2 meters per second minus 0 over our 12 seconds time span, and that gives us 0.183 meters per second squared, which will be our acceleration. And then our maximum power occurs at maximum velocity. So P is equal to mv dv over dt plus mgv sine theta. And then that equals mvd, or mv times acceleration plus mgv sine theta. And then inputting our values, we have 950 kilograms times 2.2 meters per second times 0.183 meters per second squared plus 950 kilograms again times 9.8 meters per second squared times 2.2 meters per second times sine 30, and then that gives us an answer of 10.6 kilowatts. C, our total energy transferred at the end of the track with a 1,250 meter track length. So our energy total is equal to 1/2 mv squared plus mgd sine theta, and then inputting our values, we get an answer of 5.82 megajoules. So our chapter 9 problem is problem 42, and the problem reads: a 90 kilogram fullback running east with a speed of 5 meters per second is tackled by a 95 kilogram opponent running north at a speed of 3 meters per second. And first part of the problem A reads: explain why the successful tackle constitutes a perfectly inelastic collision. And my answer is, when a successful tackle occurs, the two players stick together and is thus a perfectly inelastic collision. And the second part of the problem, B, calculate the velocity of the players immediately after the tackle. So our mass 1 is our running fullback, which is 90 kilograms, and our mass 2 is the opponent, 95 kilograms. Our velocity 1, 5 meters per second, which is I hat, and that is in the eastward direction. And then velocity 2 is equal to 3 meters per second, and our j hat direction, which would be northward. So for initial momentum, we have our p vector is equal to m1 times v1 vector plus m2 times v2 vector, and inputting our values, we find 150 kilograms per meter squared times meters per second I hat plus 285 kilograms meter per second j hat. And then we solve for final momentum, so our p final vector is equal to m1 plus m2 times our velocity vector, which is going to be 185 kilograms velocity vector. And then the conservation of momentum states that our p vector initial is equal to p vector final, and so we input our values: 450 kilogram meters per second I hat plus 285 kilograms meters j hat is equal to 185 kilograms times our v vector. And then solving for v vector, we find that our values are 450 divided by 185 meters per second in the I hat, plus 285 over 185 meters per second in the j hat. And then our final values are 2.4324 meters per second in the I hat, plus 1.454 meters per second in the j hat. Then part C in this question, it asks, determine mechanical energy that disappears as a result of the collision, account for missing energy. Our initial kinetic energy equation is 1/2 m1v1 squared plus 1/2 m2v2 squared. And then, so inputting the values, we find that our initial kinetic energy is 1,552.5 joules. And then solving for our final kinetic energy, which is 1/2 times m1 plus m2 times v squared. And then our velocity is equal to our absolute value, solving for our velocity squared, we have our velocity, we find that the square root of 2.4324 meters per second squared plus 1.54 meters per second squared is equal to 2.879 meters per second. And then finally, for our kinetic energy final, we have 1/2 times 90 kilograms plus 95 kilograms times our 2.879 meters per second squared, and that gives us a value of 766.655 joules. And then these are our vectors right here, and are indicating directions. For my chapter 10 problem, I chose problem number 30. And 30 states, a grinding wheel is in form of a uniform solid disc of radius 7 centimeters and mass 2 kilograms. It starts from rest and accelerates uniformly under the action of constant torque of 0.6 newtons times meters that the motor exerts on the wheel. And problem A starts, how long does the wheel take to reach its final operating speed of 1,200 revolutions per minute? And then we use our moment of inertia equation to find our inertia, so 1/2 times mr squared, and we get a value of 0.0049 kilograms times meter squared as our I. And then torque is equal to I times angular acceleration. And then solving for angular acceleration, A is equal to torque over our inertia. And then we input the values, 0.6 newtons times meters over 0.0049 kilograms meters squared, and that is equal to 122.44 radians squared. And then our angular momentum final is equal to 1,200 revolutions per minute, and that is equal, and that equals 1,200 times 2 pi over 60, and that would be 60 seconds, and then that is 125.6 radians. Our angular momentum final is equal to our momentum initial plus our acceleration times time, and our momentum initial is 0, so torque is equal to so T is equal to momentum final over A, and inputting the values, we get 125.6 radians per second over 122 radians per second squared, and that gives us the value of 1.03 seconds. And then part B of this question states, through how many revolutions does it turn while accelerating? And then we have the equation delta theta is equal to our momentum initial times t plus 1/2 at squared. The wheel starts at rest, so our momentum initial is equal to 0. And inputting the values, we have 1/2 times 122 radians per second squared times 1.03 seconds squared, and that gives us 64.71 radians. And then we finally we turn this into revolutions. So 64.71 radians times 1 revolution over 6.283 radians, and that gives us our 10.3 revolutions. And then for the final problem of chapter 11, I chose problem number 26, and it asked, model the Earth as a uniform sphere, and for part A, it says calculate the angular momentum of the Earth due to its spinning motion about its axis. So we have our angular momentum, L, is equal to inertia times W. I said what the W was. It's actually angular velocity in the previous question. My mistake. Moment of inertia of Earth due to its spinning about its axis is I is equal to 2/5 mr squared, and inputting the values, we get I is equal to 2/5 times 5.98 times 10 to the 24th kilograms, the mass of the Earth, and then 6.38 times 10 to the 6 meters, the radius of the Earth, squared. So our angular velocity is equal to 2 pi over t, and t is the time period. So our time period is 24 hours, so 2 pi over 24 hours times 1 hour over 3,600 seconds is equal to 2 pi over 86,400 radians a second. And then we input our values once again, and we get L is equal to 2/5 times 5.98 times 10 to the 24th times 6.38 times 10 to the 6 meters squared times 2 pi over 8,600 radians per second, and that gives us the value of 7.07 times 10 to the 33rd kilograms meter squared per second. And part B asks us, calculate the angular momentum of the Earth due to its orbital motion about the Sun. The distance between Earth and Sun Sun is stated by r, which is 1.496 times 10 to the 11th meters. Our moment of inertia of the orbital motion of the Earth is I is equal to mr squared. And inputting the values, we have 5.98 times 10 to the 24th kilograms times 1.496 times 10 to the 11th squared. And then solving for our angular velocity of revolutions of Earth around Sun, we have our angular velocity W is equal to 2 pi over t, and our time period is 365 days. And inputting the values, we have W is equal to 2 pi over 3.1536 times 10 to the 7th. And inputting our values, we find that our angular momentum is 2.665 times 10 to the 40th kilograms times meters per second, meters squared over seconds.